The broadcast is now starting. All attendees are in listen-only mode.
Well, good afternoon, everybody, and welcome to the second of today's webinars from Smart Vision Europe. My name is Jarlath Quinn. I'm an analytics consultant at Smart Vision, and I'm joined online today by my colleague Rachel. And Rachel will be checking to make sure that everybody's logged in correctly and fielding questions as we're going along. This particular webinar is focused on regression techniques in SPSS Statistics. So it's very much a primer, an introduction to regression techniques, and a demonstration. So we're looking at a couple of different regression techniques and explaining how it all works within SPSS. If you haven't joined any of these before, then a few sort of pointers and housekeeping tips at the start is that, first of all, we do record these sessions, so you listen to them again afterwards. Secondly, we do send out a copy of the slides to you afterwards, so we email out a PDF copy to you once the session is ended. If you want to find out when other events are running, you just go onto our website. If you think it's particularly useful for colleagues, we can potentially arrange a rerun of the session, maybe a private session. Just send us an email afterwards and we'll see if we can arrange that. And with regard to asking questions, all the lines are muted, so we can't hear you, but if you use the chat facility, we'll try and answer questions as we're going along. And if we run out of time or are unable to answer them, obviously we'll follow up with you afterwards. So if you don't know who we are a technology organization, and we specialize within advanced analytics. We are a premier accredited partner to IBM SAS and Predictive solutions. These are software providers in the analytical space, of course, and we specialize within predictive analytics, big data technologies, classical statistics, that type of stuff. But we also work with a number of open source technologies such as R, Python, Spark. We're a small company, but we're comprised of a team of individuals that have at least 15 to 25 years of experience working in advanced and predictive analytics. We have pretty deep experience across many different sectors, including charities, local government, retail, gaming, utilities, insurance, telcos, and media. So the agenda of the day is very much to provide an overview of regression techniques and linear relationships, show you how to perform a simple linear regression, then moving on to multiple linear regression and how we can use that to make predictions, before finally predicting response likelihood with logistic regression. So we're going to be comparing, contrasting two primary types of regression technique. So what we're going to start off is, first of all, by defining the term regression. So regression is a generic term, and it refers to a family of statistical techniques that are used to predict outcomes and generate estimates for literally hundreds of different applications. So we'll see some examples of those applications as we're going along. But linear regression is probably the oldest technique, and it's applied when the outcome in nature, the thing that you're trying to predict or trying to estimate, is a true number field. It's a continuous field or a scale field, so it would be a number as opposed to a category. And where the relationship between the fields can be described using straight lines. And if you don't know whether or not the relationship can be described using straight lines, well, you do some exploration of the data up front, and that will give you a good idea of that. So we'll be showing you how to do that in a few moments. Non-linear regression is used when the outcome itself is not linear, such as a category outcome. So you're trying to predict a yes, no, or which of three possible categories an individual belongs to. And often takes the form of logistic regression, but there are other types of non-linear regression called quadratic linear regression and cubic linear regression, that sort of stuff. And these are things which can't be described using straight lines. Relationships aren't described using straight lines. So non-linear regression is a more complex version of linear regression. And normally, when you're learning about regression, you start with linear, because that's fairly straightforward to get your head around. And then you move on to the non-linear regression techniques. So regression techniques are used for anything from modeling the relationship between promotion, spend, and revenue. So how much does every extra dollar that I spend, let's say, on advertising, generate me in revenue? Estimating pollution levels following heavy rainfall. That could be, I've actually done that where I've used linear regression, and we've looked at, pollution levels in the ocean. So we've got people going out and taking measurements of coastal pollution levels. And there is a relationship between certain types of pollution, such as nitrates and runoff from fields, such as the sorts of things that are used in to fertilize fields, etc. And you can model that. You can say, well, how much rainfall was there in the previous 4 hours, the previous 24 hours, the previous week, etc., etc., and the distance of the site to a weather station, etc., etc. You can model that and estimate the level of pollution. So the other things like predicting tourism revenue, using exchange rates and air travel costs. Exchange rates and air travel costs do affect the revenue for certain resorts, for certain countries, in fact, in terms of tourism. Predicting student test scores based upon previous test results and peer group performance. So looking at individual students and saying, well, how well did you do previously, the previous semester, let's say the previous month, or how well have other people in your peer group, in your class, performed against this, against a particular type of subject area. Estimating website hits on retweets and follower numbers. So when somebody with a lot of follower numbers retweets something and it relates to a website or something like that, to what extent does that have an effect on the website? Can you actually estimate how many hits the website will get? And things like predicting sales of barbecues based upon temperature forecasts. So you can imagine that all of these things are related. All of these examples are examples of something which is related to something else. Barbecues and temperature, website hits and retweets, student test scores, previous performance, tourism based on exchange rates, pollution based on heavy rainfall, and promotion and revenue based on the amount of money you're spending on advertising. So regression is ideal for those sort of situations. Now, regression, the term regression itself is shortened. It's shortened from the term regression to the mean, which means falling back, coalescing, if you like, towards an average. So here we have an example of a very simple relationship between the highest year of school completed by a respondent's father and the highest year of school completed by a sample of respondents' mothers. So each one of these dots represents the score for a person in the survey and for their mothers and fathers' years of education, the highest year of school. And as a result of that, there's no decimal places in it, so you get these sort of grid-like pattern appearing. But you can see that there is a relationship there, that as somebody's, the more years of education your father has, the more years of education your mother tends to have. There is, in fact, for these types of charts, a little technique called jittering, which allows you to show where all the points are clustering around. So these are jittered points, so you can see where the data is really clustering there. And in fact, if you were to take the average of one of these values, for example, if I were to take the average number of years of school completed by father against each value for mother, you can see here, you get this sort of line here. So if you're saying for respondents whose mothers have 10 years of education, on average, the fathers have about just under 10 years. It looks like they're just maybe actually no, they're both close to under 10 years there. Whereas 11 years here, maybe it's a little bit higher or something like that. There's some exception to the rule. But you can see there's a sort of average relationships there. So regression, when it talks about regressing back to the mean, it means falling back towards this averaged relationship. And in fact, this averaged relationship is normally represented by a line, by a straight line. And the straight line is put through the points, the relationship between the two variables, in such a way that it's trying to minimize the distance between each individual point and the line itself. So if you were to put a line through these points in such a way that you're trying to minimize the distance, this is the line that you get. And this is called the line of least squares. And the reason why it's called the least squares is because if we look at all the differences, the points that are above the line, the points that are above the line and below the line, and we sum them all, we added them all up, we'd find that we get 0, because of course the negatives and the positives would cancel each other out. So the convention is to square the differences. So a difference of 2 would be squared to 4, a difference of -3 would be squared to 9. And therefore, when you add up all the values, if you can make that overall number as small as possible, you have the least squares. And in order to make the least squares, you're going to have to fit the line through in a certain pattern. And obviously, the algorithm itself does this for you. It calculates the line of least squares, and this line of least squares represents the averaged relationship between the two variables. Okay, so the problem is with these lines that we put through is that sometimes the data itself isn't easily described using a straight line. So for that reason, we normally explore the data. So this first example here, this is known as Anscombe's quartet, which is used to demonstrate or illustrate some of the pitfalls associated with using a straight line. Here we can see this top left-hand corner example. This is a pretty good relationship. It's a pretty good way to use a straight line because it's kind of going through a cluster, a small number of points. However, if we have a curvilinear relationship, the straight line has no choice but to still be a straight line. It can't. It's it's not a curvilinear line, so you get exactly the same straight line, even the relationship's very different. Or here we can get exactly the same straight line, even though the majority of the points aren't quite falling on the line itself. They're actually a little bit lower than that, but the line is being affected by an extreme value. It's just important to know that extreme values can affect the line of least squares. They can affect the regression prediction that you're making. Though obviously, the fewer data points that you have, the fewer observations, the fewer records that you have in your file, the more an extreme value will affect it. If this had 10,000 data points in it, then one single extreme value wouldn't affect it that much. And even when you get basically two values, here we have basically two values, the value 8 and the value, that's probably about the value 19 or 20 here, and even then it will try and put a straight line through it. So the point is just be careful because it's an average. The straight line is an average, and just like any average, any mean value, it is affected by lopsided distributions. It's not necessarily assumed that the distribution is even. You may have much more variety in one distribution than another. You may not have linear distributions. You can have extreme values. So it is, after all, just an average. And for that reason, it's good practice to explore the data beforehand. Okay, so if we were to measure linear relationships, we want to actually measure them and say, well, this is how strong a linear relationship is. It turns out that there is a particular calculation and a particular value that helps us estimate the strength of a linear relationship. So here we have a series of scatter plots, and each of the points in the scatter plots represents a car, an automobile. And here we have two values that are related to each other. So we have the horsepower of the vehicle and the vehicle weight. So we can see that there's a few isolated cases here where the vehicle is much lighter than we would expect it given its horsepower. So maybe it's some sort of sports car, a beach buggy or something like that. But we can summarize the strength of this relationship using what's called a correlation coefficient or correlation value. And here, this correlation value here, the strength of this relationship here, is 0.859. It's very close to, it's quite close to 1. And the closer the value is to 1, the stronger the linear correlation is. If in fact you duplicated the variable and you did a scatter plot against the same variable, you would have a value of 1. Because it would, one value would perfectly predict the others. Now here, of course, it doesn't perfectly predict. You can't perfectly predict vehicle weight from horsepower or horsepower from vehicle weight, but we get a value quite close to 1, so it's quite a strong linear relationship. Whereas this one is a bit more, it's a bit more random in nature. It's the relationship between miles per gallon and the speed with which a car accelerates. So the further up the scale, the slower the car is, because it takes a lot more time to accelerate. And those vehicles tend to have better MPG. But as you can see here, the number is not as close to 1. It's much weaker. It's closer to 0. And the closer it is to 0, the more random relationship. Here we have a negative relationship because the cluster of points going in the opposite direction. And here again, if one perfectly predicted the other, but it had a negative relationship, it would be -1. Here it's -0.7. It's quite a strong negative linear relationship, which is the horsepower versus the time it takes to get from 0 to 60. And here are some other values here. Here's a value here which is almost close to 0, which is a random relationship. which is the relationship between miles per gallon and mileage. So basically, correlation values range between -1 and +1, and the closer they are to those extremes of -1, +1, the stronger the linear relationship, and the closer they are to 0, the more random the relationship is. So we can almost glance at a scatter plot and guess what the correlation coefficient is. The last example here, the fifth example, is an example of a non-linear relationship, very much like I showed here earlier on, but the correlation value is unaware of this non-linear relationship. It doesn't know that it's non-linear, so it puts a line through it, and it still comes out a fairly strong linear relationship, minus 0.671, but that's referring to that straight line, not referring to the curvy linear line. So sometimes analysts have to do things to straighten the data out, straighten the relationship out by using a curvy linear line and fitting that through, or by transforming the data. Here you can see that in order to get this relationship, I've squared miles per gallon. So very often analysts will take the square root of a variable to straighten out the relationship, or sometimes the natural log or log base 10 of a variable. So they transform it in some way to straighten out the relationship. Okay, what happens if we want to take correlations and kind of convert them into something that's a bit more meaningful, such as a percentage, rather than an arbitrary value that ranges from -1 to +1? If we want to range it from -1 to +1, what we can do is we can square the correlation. So a correlation here of 0.859, if we square it, we multiply it by itself, we get a value of 0.738, which means that 73.8% of the variation in one of the fields is shared by the other fields. And this is called the R square. If you remember, the correlation is called the R value, or Pearson's R. So if we square it, it's called the R square value. And this is useful because it tells us how much overlap there is in the variation between one field and the other. And if you think about it, you can then talk about how strong a correlation is in percentage terms. So if you get a correlation of 0.3, which is reasonably strong in social data, a lot of social data, 0.3, it's not massively strong, but it's reasonably strong. That means an overlap of 9%, because 0.3 squared is 0.09, it's 9%. So 0.4, 16%, 0.5, 25%, 0.6, 36%. You have to get up to 0.7 before you're explaining almost half of the variation in the other variables, 49%. So as soon as you start getting above 0.7, you're really starting to, there's quite a big overlap in terms of the variance in one variable accounted for by the other variable. And in many ways, this goes to the heart of statistics, because statistics is very much about the science of variation. And here we are literally talking about how much variation in one relationship is shared by another as a linear relationship. So we always have to bear in mind this is a linear relationship, and we have that restriction. Okay. So how do we go from measuring the strength of a relationship to predictive model? Well, before we do that, let's jump out and we'll look at some data and we'll look at some correlations so you get a sense of how that works. So let me just jump out to SPSS and introduce some data. So here are some data here, and each of the rows of data represents a different employee within a bank. And there's some continuous fields here. So these are fields you can use for correlation values and for linear regression. These are the ones with little rulers next to them, as opposed to category fields like this, job category. And if I wanted to explore the relationship between these, so if I want, is there a relationship between people's salary, their current salary and their beginning salary, you would expect there to be a relationship, of course. We could illustrate that, of course, using a scatter plot or something like that. So we would choose the builder tool here, and I would say, okay, well, I want to, let's get rid of that, let's delete that because we used it earlier on. I'll do a scatter plot, and I'll just do a very simple scatter plot. And I can current salary in the y-axis, beginning salary in the x-axis. I could actually put a line through it by changing that and say click OK at that point. And here we have very strong linear relationship here. You can see it's actually calculating the R square value here, which is at 0.775, very strong relationship. Let's again, but we'll try a slightly different variable. So let me chuck out beginning salary, and we'll put in age. Let's look at age and see how well that predicts it. Okay, now as you can see, if anything, there seem to be two populations here. There seem to be one group here and one group there, which is very strange. And you think to yourself, what's going on there? It doesn't look like a linear relationship. In fact, it looks like there's a slightly negative relationship. The older you are, the less you earn. And there may be reasons for that. So you might be able to say, okay, well, let's color these points. Let's try and figure out what's going on in there. And we'll color it by employment category. So if I say the employment category of the respondent. And what we're seeing here is that all these blue ones down at the bottom here, these are people in the clerical group, and the custodial group here is also in this group as well. So the managers are the ones where there seems to be a different relationship. So, you know, it's almost like there's a slightly different relationship for each of these groups, and we could actually put in, you know, we could actually fit lines in there, and it would put a subgroup. You can see different lines going through for different groups. So you can see there for the custodial employees, it's pretty flat. It doesn't really make much difference. For the clerical employees, it seems like the older they are, the less likely they are to earn. And for the managers, if anything, it goes up slightly. So we need to be aware of that when we're exploring the data. This is the importance of exploring it. If we were to look at the relationship between these variables and measure them as correlations, I can ask for some bivariate correlations here, and I'm going to ask age, education level, current salary, beginning salary, and previous experience. If I click that point and click OK, it produces for me what's called a correlation matrix, and I'm actually going to make it simpler for you, and I'm just going to pivot this. As something we can do in SPSS called pivoting. So we can go to pivot trays here and say, okay, I want to pivot this by just hiding some of the statistics, so we focus only on the correlation values. You can see age against age has a correlation of 1, of course, education level against education level is correlation 1. And we can see that there's a mirror image for education level against age, and age against education level gives us the same two values. So you only really have to look at the bottom diagonal values or the top diagonal values. You don't really need to look at both of them. And it's saying here that there is actually a negative relationship between education level and age, meaning that the older you are, the fewer years of education you have. There's a slightly negative relationship between current salary and age, which is that overall fitted line that we saw earlier on, which is basically this line I'm seeing here, is basically showing us the strength of that line. But there's some very strong correlations here, such as between current salary, for example, and beginning salary, 0.88, which when we square that, we square 0.88, we get a value of 0.775. So it's basically, that's where that's coming from. And some negative relationships here, of course, between education level and previous experience in months, which is simply saying that, you know, the more previous experience you have, the lower education level. You can see there's a very strong relationship here, of course, as we would expect, between people's age and their previous experience in months, which is a very strong relationship here at 0.8, as we would expect, because the older you are, the more previous experience you have. So this is how we're measuring the relationships and observing and investigating relationships. We're not using linear regression yet. We are not expressing these linear relationships as predictive models. And to do so, we need to think in terms of a predictive model. And to introduce that, we could start thinking about a simple example, such as how long does it take to cook a chicken? Now, this might seem like a silly example, but it's actually a really good one, because it makes us think about the limitations of predictive models, and it offers us a very simple, handy predictive model that lots of people use. They're not even aware that it is a predictive model. And this is a formula for how long it takes to cook chicken. Now, depending on what sort of chef you are and a number of other settings, if you're Julia Childs, you say 7 minutes per pound plus 45 minutes. Or if you're Delia Smith, you say 20 minutes per pound plus 20 minutes. Now, it may well be the reason why you've got these completely separate and different equations is because, you know, Julia Childs recommends cooking at one temperature and Delia Smith recommends cooking at a different temperature, so you get different equations. But basically, these equations that we've got, and they are equations, are in fact the equation for a straight line. So you've probably been taught this at school. Y equals mx plus c, or sometimes shown as y equals a plus bx. It's the same equation in a way. And the plus 45 minutes or the plus 20 minutes. This is the C here. It's the bit that's added on, or the A here. It's called the constant in the equation, or sometimes the intercept in the equation. It's the minimum value. So we're saying effectively that even if the chicken weighs nothing, we cook it for 20 minutes because you always add that on. And the 20 minutes per is the M times X, or the 7 minutes per is the M times X, or the B times X. The X itself is the weight of the chicken. So basically, you can take this formula and apply it to anything. If you said, I want to know how much more revenue I will get if I double my advertising budget, you know, you could, if you got enough examples of that, you could come up with a scatter plot and line through it and say, well, you should get a minimum revenue of, I don't know, say £5,000 or something like that. And for every additional pound you spend, you get an extra, you know, £1.20 in revenue or something like that, up to a certain level. So it would be, you can imagine that the equation here would be, you know, 1.2 times X plus, you know, 5,000, which would be our equation. So the key here is that linear regression is as simple as that. It is a linear equation. And of course, the straight line that we're seeing in the charts that we're seeing earlier on here in these charts, as we're putting these straight lines through them, like this, this is the equation that we're getting out. This is the same equation. So the more the line fits that cluster of points, the more accurate, of course, the equation is. Okay? So when we run a linear regression in SPSS, it gives us these values. You know, it actually tells us what the coefficient is, what the M is, or what the B is, and it tells us what the constant is. So it tells us, you know, how to actually predict the outcome. Although it will do it for ourselves. So here, for example, we've got highest year of high school completed by mother against father, and the R-square value is quite weak at 0.38. It means that there's 38% overlap between one field and the next. And it's saying that if you wanted to predict the number of years that a father has of education based upon the number of years of mother, here is the equation that you get for that. That's called a simple linear regression equation. Simple because we're only using one variable to predict another, not multiple. And it's saying that basically, if somebody's mother has 10 years of education, then, and you want to predict how many years that the father has, well, you'd multiply 10 by 0.74, which would get you 7.4 years of education, and you'd add on 2.89 on the end of that. So it's going to be just over 10 years of education predicted for the father. That's what the prediction is going to be. So let's look at a demo of the regression in IBM SPSS Statistics. Let's do a quick look at that, and we'll look at how we can do this. So far in this data set here, we haven't been predicting an outcome, but we have been looking at trying to estimate the relationship between variables. Let's assume that we're trying to predict this key field. Let me just move it right to the end here so we can really focus on it and make sure that this is the thing that we're looking at. And I'm going to be using initially some of these continuous fields to predict it. To do so, if I go to Analyze here and go to Regression, you'll see that in fact there are many types of regression that one can do. And this is partly because we've got the regression module. It's also because we're using some of the extensions from the extension hub. So it turns out that within SPSS Statistics, you can link to a central web-based repository of additional routines, which are based on Python or R, the Python or R open language, and you can install them directly to SPSS, which is what I've done. So these are the additional routines that have been installed there. Some of these routines are already pre-installed and they're based on R or they're based on Python, so you can see them added here. But if I just pick the standard one, the most classic one, which is just a linear regression, then we can click on that, and here's linear regression. And we say, okay, well, I want to predict current salary. I put that in there. And I'm going to use beginning salary to predict that outcome. And if I click OK at that point, that's all I need to do here. There's a lot of other options, of course. If I just click at that point and say that that's fine, what you'll find is it produces some output. And this output is remarkably standard across different tools. You get very similar output, even if it isn't SPSS. But what you normally get, if we focus on the first box here, you can see there's a number of different bits that are kicked out to us, these different pieces that I'm just highlighting now. So we can see that the variable beginning salary was entered into the model, and then it gives us a model summary. And the model summary shows us the correlation, which is the R value between beginning salary and current salary. If we square that, as we know, we get 0.775. 77% of the variation in people's current salary can be accounted for or predicted using people's beginning salary. And the adjusted R is the one which is actually normally quoted in research. This is an adjustment based upon the sample size. It's always slightly smaller than the R-square value. It's looking at the variability sample size, so it's slightly smaller. And it's a more realistic estimate, so it's saying that, you know, it's about 77.4% overlap between the two variables as opposed to 77.5% overlap. And then we get this strange thing called an ANOVA table, a sum of squares. This is a test, and it's a test saying, you know, is it better? Is this model that you've produced, is it actually better than using what's called an intercept-only model, which means just taking the average? You know, if I just took the average of beginning salary, let's see what the average. Sorry, the average of current salary. Let's see what that is. It is it's 17,000. If I just said that's my model, I'll just predict everybody to be on about $17,000, if you like, or a minimum value or something like that. Is this actually better than that? And normally we would expect this value to be 0.000, which just means that we reject the null hypothesis that it's no better than taking an average. And you know, you hardly ever see this anything other than significant. So you can kind of ignore it to a degree. Where it's useful is when we come to comparing one model to the next, because this is a good way of us assessing the overall fit of the model using the F value. And it's a way of us saying whether or not the overall model is better than a wild guess, if you like. So we can usually not ignore it, but we don't have to pay too much attention to it because, as I say, it's normally significant. The heart of the regression model is down here, and in particular, it's in this column here. You can see here it says constant and beginning salary, and there are two numbers associated with constant and beginning salary. So the constant is the 20 minutes is the plus 20 minutes or the plus 45 minutes. It's the minimum value. It's the point at which the value crosses the x-axis. If you look at over here at the earlier chart we were producing, it's basically saying that this is the point at which it crosses the x-axis. It's the minimum value in the model, if you like. We're just using the model, and it's saying, you know, if you assume that everybody makes at least, you know, $1,900, you know, so you make it just under $2,000. If you take their beginning salary and you roughly double that, so 1.9. So if they got a beginning salary of $10,000, that means for every $1 you get in your beginning salary, you end up with nearly $2 in your current salary. Okay, so it's saying that if you have a beginning salary of $10,000, you're probably on $19,000 plus $1,900, so close to $21,000. It's probably it. And then we have the standard error metric. This is about the reliability of this, or how much error there is associated with it. The less important that term is, that part of the coefficient, the larger this value is. And we even have a statistical test to tell us whether or not these two values, based on a t statistic, whether or not these two terms are actually contributing to the model. So if I put in something that was random in there and it wasn't contributing to the model, this would be non-significant, it would be above 0.05. You can see here the constant here is quite close to 0.05 because it's the weakest part of the equation. It's just the add-on bit. But certainly beginning salary is very strongly related to it because it has this beta value here of 0.88. We'll keep an eye on this, but you can see it's exactly the same as the R value. And when you only have one variable in the model, then it's always the same as the R value because it's the amount of unique variation that is shared with the dependent variable. As we add more fields into the model, the amount of unique variation, this number normally gets slightly smaller because there is some of the variation is shared with the other terms. So it's called a partial correlation. It's kind of showing you the pure correlation. Let me illustrate it by adding in another field. So I'm going to go back here and we'll add in another field. And I'll add in, I will add in, let's see, let's put in something like previous experience months since hire, because that might be important. How long you've actually been in the job might affect things. Let's see if that affects things. If I click OK at that point. Now we have, let's compare the two. So here we have an adjusted R-square now of 0.78, whereas beforehand it was 0.77. So it's only added a tiny amount, it's only added percent to it. That's partly because beginning salary already has such a strong relationship. But it's 0.78 now, 78%. Of course, the ANOVA table's still the same. There isn't much. The beginning salary beta coefficient hasn't changed very much. It's 0.882. So it's ever so slightly smaller than the R value here, because there's a tiny overlap with months since hire. But basically, we're saying if everybody had the same months since hire, if everybody was, you know, exactly 10 months since hire, or 12 months since hire, if everybody had the exact same value, this is the amount of correlation we would see between beginning salary and the target of current salary. But months since hire itself add a little bit to it. It's about a 10%. You can almost think of this as almost like 10%. I'm saying about 10% of this contributes towards unique variation towards our overall prediction. So there's a bit of an overlap there. And they're all significant. So the constant now is now a negative value. We're actually taking off $12,000. So now we'll be multiplying the beginning salary by 1.9, which hasn't really changed very much. And for every month since hire, you get an extra $72 on average. And then whatever that number comes to, when we add that up for every individual, if we take off $12,000 at the end, that will give us our estimate. So what happens if we want to add them all in? If we start to add in things like age and education level, and, you know, say something like previous experience in months and stuff like that. And so I'm really starting to treat it a bit like a cement mix now and chucking everything in. The R-square value now has jumped to 0.8. And what we're seeing here is that as we add them in, for example, previous experience in months is not significant. You know, it's not contributing anything. It's a very small value. It's actually saying that if we were to take it literally, we'd be saying for every extra month of previous experience, you earn $8 less. But it's, you know, it's really not. It's not adding very much to it. So we might want to take that out. Age is marginally adding to it. We can see that the values of the unique variation that they're contributing to it is quite small. Not really contributing a great deal. So one of the things you can do is you can do something called forward or stepwise or backward methods. If you go for forward here, it will put in significant variables one at a time, and will build the equation up. So you can see here it builds a 5-step equation, and it says, okay, I'm going to add in beginning salary, I'm going to add in beginning months since, and then I'm going to add a month since hire, and I'm going to add in education level, then I'm going to add in age, and you can see it stepping up from 0.77 to 0.81 in terms of 81% variation, and it shows us, of course, 5 different ANOVA tables because we're building 5 models, and it shows us 5 different sets of coefficients until we get to the final model here, where it adds in a constant, a beginning salary, previous experience in months. In fact, previous experience in months should be taken out by this stage, and you know, adding it in, it was significant. Look at this, it was significant in the previous step, but when we added in age, it became non-significant, and this is because age and previous experience, as we know, are so strongly correlated with one another that they're pretty much measuring the same thing. Okay, so what happens? What if I did it the opposite way around? What if I did backward, where I added everything in and it took out the non-significant stuff? Well, if I do that, it actually comes up with a very different model here. It says, okay, well, I'm going to add everything in, only 2 models, because I add everything in, force everything in, and then I remove previous experience, excluded variable, model number 2, and everything's still significant. So that's a kind of a purer model. Okay. Now, if we look and see what this is actually doing, I could say save, and I could say save unstandardized. That means raw predictive models, predictive values. I could click OK, and it could add that in. So it could actually add that in. Here's the previous experience. It's been added in, and then I could say this is the prediction. This is the actual. Sorry, this is should be, I'm trying to predict this value here. Not previous experience, this is prediction. This is actual, so here's the actual value, this is the prediction. Look how close they are to one another. If we want to map that and show how strongly related they are to one another, of course, all we've got to do is take current salary, multiply that by its unstandardized value, and this is the relationship between the prediction and the actual. And we can see it actually funnels a little bit. This is called, the technical term is heteroskedastic. It means it funnels. It's harder to predict the values for manager than it is for these other groups down here, where it's kind of tighter. But it's still a pretty strong relationship, and you know we know what the correlation is between these 2 points because it tells us here that the correlation is actually 0.9, and that gives us adjusted R-square of 0.81. Okay, so that's one way in which we can port the model. There's another way in which we can port the model, and we can say, okay, well, I can save the model. I can actually save it as a file and apply it to another data set. But before I do that, I just want to point to a couple of things here, which is that if you have binary fields, if your fields like this, fields that only have 2 values, you can't actually add these in to the model itself. So here we have the value of 0 means that somebody's white, and the value of 1 means that they're in a minority group. So we could actually add in that value. Let me read linear regression again. I'm going to switch off the save here because I don't want to save it. And add that in. Click OK. That puts it in. Will it go in? Let's see. Well, interesting enough, it actually excludes it. It takes it out because it doesn't, whether or not you're a minority, doesn't help or doesn't add enough to the model, so it excludes it, and then it also takes out previous experience. What about gender? We've got a field here, gender. Surely I should add that in. I've got linear regression here. Watch what happens if I try to put that in. It doesn't let me, see? This is because this is a string field, and it has letter codes. It must be number codes instead. So I could turn this into a numeric field by clicking here and saying, okay, let's use the automatic recode facility. Let's create a variable here called sex of employee. It's not that easy. And we'll say start to recode from the lowest value to the highest value. It doesn't really matter what order they're in. It creates a new field for me here, and the values are 1 and 2, male and female. Let's add that in, and we can add that in. Let's see if that works. Now it's accepted that, and let's see. It has actually added the variable gender of employee to it, and it's basically saying here that if you're a man, as opposed to being a woman, because it's always a higher value, men are coded as 2 here rather than 1. If it was all the way around, this would be a negative number. So if you're a man rather than woman, you can expect an extra $2,259. So that's the effect of being a man as opposed to a woman. What if I wanted to add in a category field like this job category, and take account of that? Could I add that in? Well, I could add it in, but I can't add it in this format. What you have to do is you have to turn this into a series of binary fields. Are you a manager? Yes, no. Are you clerical worker? Yes, no. Are you custodial? Yes, no. I need to add those in as a series of different fields. And to do that, I do something called dummy coding it. So there's a procedure that I can run which will transform the data and says create dummy variables. So if I create this field here and say employment category, and I'll just call it job. I'll just call it job here, and it's going to create for me a series of fields. If we look along here, which is simply are you saying are you a manager? Yes, no. So this is are you clerical? Yes, no. Are you a manager? Yes, no. Are you custodial? Yes, no. And I don't have to add all 3 of them in. I only add in 2, because if you're not in job 1 and you're not in job 2, then you must be in job 3, and vice versa. So if I add these into the linear regression now, I say, okay, let's put in everybody but custodial. Sorry, everybody but clerical. And click OK at that point. And it adds these fields in. Let's see if they get added in. They do get added in. Minority classification and age is still put out. And it's basically saying that if you're a custodial worker here, as opposed to being a clerical worker, you can expect to earn $6,734 more if you're a manager, you can expect to earn $11,000, 226 more than a clerical. So it's almost like it's adding an extra constant onto it. So it's the effect of not being clerical and being custodial is to give yourself an extra $6,700. The effect of being a manager and not being clerical is to give yourself an extra $11,000. And now the R-square is climbing. The adjusted R-square here is gone down to is 8.84. We can see that the, let me just see you can see that R value here is 0.918. Now you'd have to ask yourself whether or not adding in all of these extra fields is worth it. You know, if you're going to add in a lot of extra fields, because we're getting quite high R values. All the backwards method is doing is just getting rid of the non-significant fields. But you know, it is technically a better model than previously, although it is a more complex model because we have more terms in it, and it is dominated very heavily by beginning salary. So there's a lot of diagnostics we could do at this stage to, you know, to help us predict this outcome. And in fact, if I wanted to save this as a this model that I'm producing as a file, I'm just going to save it as a file and call it regression webinar. And I'm going to, let me just see where I'm going to put it. I'll put it into, it's a folder here called regression. So just click regression webinar, hit save, hit continue, run the procedure again. It writes out that model as a file. If I then delete salary, literally delete it, and imagine that I've got some new data where I'm trying to predict people's what their salary is based upon their beginning salary and all the other information. I can go to utilities here and I can call up something called the scoring wizard, and I can look for this regression webinar example that's just found, and it matches the fields that it needs in order to predict that outcome. It's going to produce for me a predicted value, and hit finish, and it's applied this saved model now to this data set. Okay, I've just got time at the end here to compare and contrast this linear regression modeling approach with a completely different approach, which is logistic regression. So with logistic regression, we're trying to predict not a continuous outcome, but a category outcome. It is more complex with regard to interpretation. And the reason why it's more complex is because it's non-linear. So logistic regression allows you to predict things that linear regression can't, such as the response to a marketing campaign, some of these credit risk, or whether or not they are a credit risk or not, whether or not a subscriber is likely to renew a service, risk of equipment failure, or how likely it is that a patient will be readmitted to hospital, or whether a charity donor will switch to direct debit from cash donations. Now, these outcomes are not continuous numbers, so standard linear regression doesn't work. And when the outcome consists of more than two categories, when an outcome consists of two categories, we use what's called binary logistic regression. When it consists of more than two categories, we actually use a more complex form called multinomial logistic regression. Logistic regression gets around the limitations of describing relationships with straight lines by using a special sigmoid curve. And this curve relates to odds, to odds versus probability. I can't really have time to go into the technical side of it, but suffice to say that you know, what it's trying to do is discriminate between two conditions, a 1 and a 0 here. And if we imagine the probability of somebody responding to an offer, as we increase the discount level, they flip from, you know, from being a very low likelihood of responding to a higher likelihood of responding. So going from, they move up this likelihood of responding scale here. And this sigmoid curve, which is the relationship between the odds of them responding and the discount, it helps us to do that. So the downside of that is that when we produce our coefficients table in SPSS, we can't interpret in terms of 20 minutes per pound or that sort of thing. We can't say for every 1 unit increase you're going to have X% more likely to respond, because it's giving us the result in terms of the law of the odds, which is a very hard thing to think in terms of. Nevertheless, we can convert that using a special transformation function known as a link function, and it produces for us a probability value of an outcome. In this case, the probability value will be the probability that somebody is in the higher group of this target field, which is whether or not they will accept a news channel. So there's this sort of channel. This is very old data from a television company, a cable television company that was offering a special news channel subscription, and people, they were trying to figure out who was going to respond to it. So they have information about people who have responded to it and have accepted this additional service, and they have their education level, their gender, which is numeric here, their age, and the hours spent watching TV per day to try and predict whether or not they will accept the news channel. So this time we have to go to analyze, we have to go to regression, and we go down to the binary logistic regression. So we're doing binary logistic here. And we put in accept news channel service, that's our dependent, our 2-category outcome variable here. And we put in our other fields here. I'm going to throw them all in. You can see that you have this enter method, forward method, backward method. Let's do forward this time. I'm going to use forward LR. And this time I'm actually going to ask it to save something. Let's save a couple of points for us. We click OK at this point. It takes longer to run it because it's actually doing a lot more in the data. And it starts off telling us how well it's doing in what's called a classification block table. And it basically says, well, I start out with an intercept-only model, which basically says I'll just predict everybody to be a no, because there are more no's than there are yeses. And if I did that, you know, you can see I would be right 51% of the time. So that's kind of what we're trying to beat here. We're trying to do better than this 51%. We're trying to start to predict some of the yeses and predict some of the no's. So as we do that, it says, okay, I'm now adding in variables into the equation so that the constant goes in, which is just basically says, okay, I'm going to add in a constant of 0.5, if you like. So I'm just going to give this weird value of minus 0.05. That's the log odds. And it's telling us that that's not great. It's not terribly. It's not even significant. So that doesn't help us. It's not much better than just predicting everybody to be 51%, because it's pretty evenly balanced, 224 versus 213. And it says, okay, here are all the variables that aren't in the equation. And we can see that education level in years is not significant, and hours TV per day is not significant. So it adds them in, step 1, step 2, step 3. And here we can see, as we're adding in these fields, as we're adding in and building the model up, it's giving us some pseudo R-square values, which aren't, they're kind of not exactly the same as the R-square values that we saw earlier on, but the larger the number, the better the fit. We can think of that way. So for whatever is added into the first model, it's saying, okay, I'm doing much better now. I'm predicting 73% of the no's and 59% of the yeses. And then the next model, it's doing better. It's predicting less of the no's, so 68%, but better on the yeses. And then the last model, it says, okay, I'm doing 69% of the no's and 62, nearly 63% of the yeses. Overall, that's an accuracy of 66%. And here are the variables in the equation. And if we look at the last one here at step 3, these values here we can't interpret, okay? We can't. These are the log odds values. But if we look over here at the exponent b, exponentiated b, what we're saying is that you are, if you're female, basically, which is the higher group, you're half as likely, because that's nearly 0.5. You're half as likely to accept it, to accept this service, okay? This value here says for every 1 unit education level in education, you are 1.1 times more likely to accept it. And for every year extra, you are 1.06 times more likely. So here we're talking in terms of times. If that value was equal to 2, we're saying you're twice as likely to accept it. And this is how we interpret the model and see the effect on which variables are correlated most strongly. By looking at the exponentiated value here, we can see here that the variables were not in the equation are education levels, education in years, and hours per TV per day. That gets hours per TV per day gets taken out at that point because it's not significant. It's the one that's not been used. So That's not added in. It's the last one that doesn't get added in. What do we get in the prediction? Well, in the prediction, instead of getting a continuous value, we get a probability value here. Here's the probability value, and it's telling us the probability that you are a yes. And obviously, if it's greater than 0.5, it says, yeah, there's a 67% chance this person is a yes, so it predicts them to be a yes. There's a 19% chance this person is a no, so it predicts them to be a no. There's 75% chance that they're a yes, they're a yes. So if you're just above here, this is just above 0.52, so they're a yes. So very often people will use the probability value and say, well, I'm going to look at the probability of them being a yes, and I'll use that to select people for a mailing campaign or to make a judgment on whether or not they are a good credit risk. So although the output is somewhat different, there are certain commonalities between linear and logistic regression in terms of interpretation. It's just that it's not a linear model, so we can't directly interpret the B coefficients in the same way that we would in a linear model. Okay, so the IBM SPSS regression model opens up all these different types of regression techniques to us, including binary logistic regression. And it's worth investing in if you wish to do that type of regression, if you want to go beyond simple linear regression. Linear regression is in the base version of SPSS. And with regard to getting hold of the software, you can buy the software directly from us, and we can assist with pilot implementation of many different software tools. But if you want to actually buy SPSS Statistics software, you can just go straight onto our website and do so. We also offer guided training consulting to help you develop in-house skills, delivery of classroom training courses, identification of recruitment of analytical skills, and generally offer no strings attached advice, as well as technical support services, telephone-based and web-based services around SPSS and SAS. I do hope you find that useful. We have another webinar coming up in around about an hour's time at 3 o'clock when we're looking at a sister product of SPSS Statistics. We're looking at SPSS Modeler. In the meantime, we look forward to you logging in again. Thanks for joining us this afternoon.